So in this picture, it shows that a dancer moves around a path, as the one shown in the figure, with constant speed. And that's actually a critical part of this problem, is that it's at constant speed. Which of the following best represents the magnitude of the dancer's acceleration as a function of time? So as a function of time, we're going to do the acceleration and time, and I'm going to mark off the time when they hit specific points. So I'm going to say at point P, so t sub p, that's when they hit that point P. There's going to be a t sub q, followed by a t sub r, followed by a t sub s, and followed by a t sub p again. The second time we hit this. And this is my time axis. Seconds. So when they go around this path from P to Q, when we go from P to Q, then we know that we're going at a constant speed in a constant direction. So we remember that our velocity is both a speed and a direction. So we know that for constant speed at constant direction, our acceleration is 0. And same thing from R to S. We're back to 0. In those cases, we both have constant speed with constant direction. Constant speed, constant direction through that area. However, when we get to this curve right here, we know that this curve has some radius on it, and we know that our velocity vector is going to be constantly changing. It's going to keep the same speed, but the direction is going to change, which means we need an acceleration. And the acceleration that changes directions or causes circular motion is given by the centripetal acceleration. Since we have a constant radius through here, and we're moving at constant speed, this value, the magnitude, is going to be a constant value. The velocity or the speed doesn't change going around the curve, and the radius of the curve doesn't change, so that means our acceleration around the curve has to change. And just connecting these to make it continuous. Same thing over here. Same curve, same speed provides us with the same acceleration. So this part right here, this is what we would label as AC for that value. So we go around with 0 acceleration, then we do centripetal acceleration, back to 0 acceleration, and then back up to centripetal acceleration, and then we just keep repeating ourselves as we go around that path. So not too tricky of a problem. We just have to remember that an acceleration can change both a speed and a direction, and in this one, the direction was really the part that we changed the most on.